Swayam Prabha. Digital India. Educated India.
Let us continue our discussion on compressible boundary layer equations in this lecture. So, in this lecture we would like to look at the 2D laminar compressible boundary layer equations. We have started doing that already from the previous lecture. We would look at the concept of self-similar and non-similar solutions of boundary layer equations. We would recapitulate the Blasius equation in the context of incompressible flow past a flat plate, and we would also start looking at transforming the compressible laminar boundary layer equations, the x and y momentum equations in this lecture. This is what we were doing in the previous lecture. We did the order of magnitude analysis of the x momentum equation, and thereby we saw one of the terms dropping out as being a small term. Then we looked at the y momentum equation, and as we applied the order of magnitude analysis, we found that it gave us the familiar outcome that we saw for incompressible boundary layer for a flat plate in the laminar region given by the Blasius solution, but that holds good as long as the m infinity is not extremely high, and therefore, in the supersonic Mach number range this is quite alright, while in the hypersonic range the del p del y in the non-dimensional form that we see over here could be of order 1. It may not be very small. We continue discussing the laminar compressible boundary layer equations, and we now take up the energy equation. So, what we need to do is have a look at the energy equation where we left it and substitute in place of the specific internal energy this expression H minus P V, where V is the specific volume, or it could be H minus P by rho if you want to state it in terms of density. So, that needs to be substituted in place of specific internal energy. After that, subtract the momentum equation, multiplying it by the velocity from the energy equation which has resulted from step 1. Once you do these steps and then move on to the order of magnitude analysis like we did for the continuity and momentum equations, we would be able to obtain the boundary layer form of the energy equation, and in dimensional form this is how it looks. So, you can of course make out that some terms have dropped out, but it is left to you as a small homework problem to do this derivation and also figure out that which terms become small when you do the boundary layer analysis. So, now if we put everything together, we have the boundary layer form of all these equations in dimensional form, of course mentioned over here. The continuity equation, the x momentum equation, y momentum equation, which is of course true when it is not for a very high Mach number, and then comes the energy equation. Of course, once you put this outcome into the x momentum equation, that would mean that the pressure would now become purely a function of x, and in place of a partial derivative we write it in the form of an ordinary derivative. And what we mean by subscript E is that it comes from the inviscid flow which lies beyond the boundary layer. Now, in the boundary layer equations we saw that pressure depends on the inviscid solution, the P E as we say, and it exists outside the boundary layer, and it has to come from an inviscid solution that we perform. And pressure becomes purely a function of x, it loses its dependence on y. and being a function of x, it would then depend on the surface geometry alone. Now, since the pressure would be known from the inviscid solution, the equations 1 to 4 contain 4 unknowns u, v, rho and h. And where do we get the pressure from? We get it from the Euler equation. When we apply the Euler equation, this is how it looks. In differential form, and this can be applied at the edge of the boundary layer, and that is how the pressure will be input into the boundary layer equations. The properties mu and k which lie in the equations are dependent on temperature, and for a calorically perfect gas, once you have the enthalpy solution, you can derive temperature from this relation where Cp is a constant. Effectively, equation 3 does not contribute anything independently. So, it does not act as an independent PD at all, and hence the conservation equations reduce to 3 in number effectively, since you have already replaced the pressure gradient in terms of the PE. And now it contains 4 unknowns, as we already mentioned. If you go back to the previous slide, these are the unknowns we are talking about. So, you have one less equation effectively. In order to make up for this gap and complete the system of equations, what do? You invoke another 2 equations, whereby we will be able to balance the number of equations we have and the number of unknowns that we solve. A very important ingredient is the equation of state, and for a perfect gas it looks like this: P equal to rho R T. Additionally, we bring in the relation for enthalpy in terms of temperature, and for a calorically perfect gas, which is going to be true for the supersonic Mach number range, the Cp will be expressed in terms of the specific gas constant and gamma using this relation where it remains a constant, and then you effectively solve the equations 1, 2, 4, 5 and 6, which are 5 in number, so that you can solve for u, v, rho, t and h. Those are your 5 unknowns, and you now have 5 equations. How do you solve the equations? The solution depends on the boundary conditions that you impose. One is on the wall side, the other is at the edge of the boundary layer. Once you cross the boundary layer, what lies there? So, it is basically in the inviscid region. At the wall, since you are talking about a no slip condition, since it is a viscous flow you are talking about, thereby u and v are 0. It is a 2-dimensional flow, so 2 velocity components set to 0. If it was a 3-dimensional boundary layer we were talking about, then there would also be w equal to 0 additionally to be imposed. Temperature can be imposed in 2 ways. One is, if we maintain a constant temperature at the wall, it would be an isothermal wall condition, in which case T is equal to T wall. It will be set to a certain value. While if it is an adiabatic wall, which is basically a thermally insulated wall, which does not allow any heat transfer, then the temperature gradient normal to the wall would be 0 when you are right at the wall. So, that gives us the adiabatic wall condition. So, we therefore have a thermal condition at the wall imposed. Now, moving to the edge of the boundary layer, which would happen at a large value of y, which is not known a priori, of course. So, y tending to infinity, we should be able to asymptotically reach this condition that u tends to u e and T tends to the free stream temperature that we are working with. So, it is basically the free stream static temperature. Now, the boundary layer thickness will turn out to be a function of the similarity parameters, and it is also not known in advance. It emerges as a part of the solution. So, when we solve the partial differential equations in a coupled manner, using the boundary conditions that we have discussed above, then automatically the flow solution will come up and thereby the boundary layer thickness will also get determined, and the edge will be found to be at a large distance away from the wall. Of course, this distance is not supposed to be very large compared to the characteristic dimension of the problem. That is also something that we have to remember. So, if the characteristic dimension of the problem is C, then the thickness is much smaller than C. Now, let us discuss some issues at hypersonic and hypervelocity Mach numbers, which will have an impact on the boundary layer theory that we are trying to develop. So, as m infinity becomes large, we know that del p del y becomes non-zero, and therefore, the boundary layer solution will not remain valid anymore. In such a case, we have to go for a complete viscous flow solution using Navier-Stokes equations, and such equations when solved, they do not assume any value for del p del y a priori. It is solved automatically when the governing conservation equations are calculated. As a consequence, the thin shock layer that we are familiar with at hypersonic conditions, which lies between the body and the shock, may turn out to be completely viscous. This is one consequence. At large m infinity, there is severe viscous dissipation within the boundary layer, which is going to lead to high temperatures. This can cause chemical reactions within the boundary layer. Obviously, Cp would no longer be constant. Diffusion of chemical species would occur. Energy changes would be caused when chemical reactions occur. So, these have to be accounted when we solve the boundary layer equations at high Mach numbers, and therefore, in all probability there will be significant change in the equations which we have to be incorporating, and in all probability we will not be able to retain them as such. We will have to go for Navier-Stokes equations, including the effects of diffusion of chemical species and energy changes due to chemical reactions. There are some flows which occur at very high Mach numbers, which still are associated with low total enthalpy values. Example, some of the flows that we see in wind tunnels, if the flow in the stagnation chamber is not preheated. So, such high temperature effects like the ones we discussed over here are not seen in these flows, because they may be high Mach number flows, but not very high stagnation enthalpy or total enthalpy flows, and therefore, they may be for all practical purposes treated as cold flows, not hot flows. Compressible boundary layer theory, let us try to go a little further, and we are of course talking about the laminar flow. We are considering laminar boundary layer equations. We are talking about calorically perfect gas. We are taking Cp, Cv, gamma as constants. Fluid dynamic effects of viscosity and thermal conductivity, they are being addressed at moderate Mach numbers, where high temperature chemically reacting flow is not considered. Therefore, we are primarily concerned with the hydrodynamics of the flow. The boundary layer equations would be transformed from the physical space, that is the xy space, to a psi eta space in order to explore the possibility of self similar solution. The motivation is that we looked at Blasius solution, which is the laminar incompressible boundary layer solution for a flat plate, and there we did see self similar solution coming up. So, our motivation is that the compressible boundary layer equations, whether they would also manifest the self similar behavior or not, at least for certain kinds of flows. Flat plate is definitely one of them. Let us try to recapitulate what we mean by self similar and non similar boundary layer profiles. In the physical plane or space, this is how the boundary layer grows. This is the leading edge of the flat plate, and at two different stations x1 and x2 respectively from the leading edge, we have shown the velocity profiles. We see two different boundary layer thicknesses delta 1 and delta 2, and we find that the velocity profiles are distinctly different, but the free stream values are the same u e for the given problem. So, when we look for self similar solutions, we try out transformation functions which can translate this flow problem to a transformed plane where the velocity profiles collapse to a single one. That means, as I move from one station to the other, though in the physical plane the velocity profiles look distinctly different, in the transformed space they look identical. So, if x1 maps with xi1, x2 with xi2, these are the two locations from the leading edge that we are looking at the velocity profiles, and the first profile here maps with the first one here, the second profile here maps with the other one here. Then you find that under the effect of the transformation functions, they look identical, and they thereby lose their connection with the xi coordinate and become purely functions of the eta coordinate. So, if that is possible, then we have the so called self similar boundary layer velocity profile, where it does not have any dependence on xi. However, if we fail to find such transformation functions, we may land up with non-similar boundary layer solution. It is in the transformed plane, but the velocity profile turns out to be function of xi and eta both, which means the conservation equations that we see in the transformed plane, they remain as PDEs, because they have dependence on two independent variables, while here the governing equations will turn to ODEs, because they depend only on one independent variable. As a consequence of a non-similar boundary layer, the velocity profiles in a transformed sense depend both on xi and eta, and therefore, the velocity profile at xi1 is not identical to the one at xi2 or xi3 and so on, and that is what is manifested here. A quick recapitulation of the Blasius equations, which are the primary motivation behind all this discussion, is that was the equation which was evolved for solving laminar incompressible boundary layer on a flat plate, and it all evolved from Prandtl's boundary layer theory for incompressible steady laminar flow past a flat plate with constant density and viscosity. So, Blasius introduced some similarity variables by means of which the self similar solution of the boundary layer equations was achieved, and this was transformational in the sense that this was a new technique introduced and it really changed the scenario of fluid mechanics. So, Blasius introduced eta, which is y by delta, delta being the boundary layer thickness, and he took boundary layer thickness to be proportional to under root nu x by u, where nu is kinematic viscosity, u is of course the free stream velocity. The other similarity variable that he introduced was psi, the stream function, in terms of another function f, which is purely a function of eta, the wall normal coordinate in the transformed space, and this is a coefficient under root nu capital U x, and under this influence of two similarity variables, he looked at the three conservation equations and transformed them into one ordinary differential equation in the function f. So, as is evident, it is a third order ODE, and he specified that this should be the boundary conditions to be imposed to solve it. So, at the wall f 0 is 0, f dash 0 is 0, and at the far field, that means at the edge of the boundary layer, the f dash should be equal to 1. When it comes to the laminar compressible steady boundary layer equations, then we find that we need a different transformation which is called as the Lis-Dorod-Nitsin transformation, named after two scientists who had important contribution in this direction, and we thereby have two functions xi and eta defined over here. So, as you can see, xi is purely dependent on x, while eta is dependent both on x and y. A little bit of the transformation mathematics which we need to be a little aware of. So, we transform the independent variables x and y in terms of xi and eta, because we are transforming the problem from physical space to a transformed space. Therefore, these metrics are basically required. Del del x and del del y are now represented using these equations by the chain rule, and we can show easily that del del x finally reduces to a form like this, while del del y reduces to a form like this. One of the terms over here drops out because del xi del y is 0, since xi is purely a function of x. Then transform the dependent variables by introducing a function f which is dependent on both xi and eta, and we will show later that it is related to the stream function psi. We define u by ue, which is basically the ratio between the streamwise velocity within the boundary layer at any location eta or y scaled with the free stream velocity ue, and it is given by del f del eta or f dash. Of course, f dash at the wall has to be 0 because that is the no slip condition, and again in the far field where eta tends to infinity, it has to be 1, which is the edge of the boundary layer. Now, del u del xi will turn out to be f dash del u e del xi plus u e times del del xi of f dash, and similarly you can find del u del eta. And in the del u del eta expression, again one of the terms will drop out because u e is a function of x or xi only, and therefore its eta partial derivative will be 0. Therefore, it turns out to be only u e times f double dash. So, why are we taking the trouble of doing all these transformations? Because if we want to transform the conservation equations from the physical space to the transformed space, then these derivatives have to be taken care of. Now, introduce the stream function xi, which is a function of x and y, and by definition, as we know, in the compressible flow del xi del y will be rho u, del xi del x will be minus rho v, and then the del xi del y, which is rho u on one hand, can be represented in terms of del xi del eta in the transformed space, and again rho u can be represented like this in terms of f dash. Therefore, put together del xi del eta will have a representation like this. Now, if you integrate this relation, there will be an integration constant which can depend on xi, and we can argue that if we apply the wall boundary condition, then k xi can be shown to be equal to 0, in which case you have a very nice compact relation between xi and f related by xi equal to under root 2 xi times f. So, here you have psi in terms of under root 2 xi times f, and now if you take a derivative of psi, which is the stream function. So, this is psi while this is xi, and when you take a derivative you get a form like this. Now, if you transform the x momentum equation using all the above relations that we derived, you will see that they can be plugged in into the different terms of the x momentum equation, and additionally we recall that the pressure gradient term has to be evaluated by invoking the Euler equation at the edge of the boundary layer, and that governs the inviscid flow beyond the boundary layer. And once you do the transformation, the transformed boundary layer x momentum equation in the 2D compressible flow sense will look like this. So, what do you find over here? You find a new entity which we are calling as capital C. What is it? It is rho times mu by rho e times mu e. So, rho times u is at any particular eta, which is of course y in the physical space, while rho e and mu e, these are at the edge of the boundary layer. So, it is at y tending to infinity or eta tending to infinity. Actually, it is the delta, the boundary layer thickness, but we do not know that a priori, and therefore, we try to set these limiting values. Again, notice that this equation contains a lot of these terms involving the derivatives of f. When you have a dash or a double dash, it basically means that you are taking a derivative with respect to eta, while if it is with respect to xi, you will have the terms represented like this, which basically means that this equation has dependence both on xi as well as eta. We have mentioned the x momentum equation once again over here. The transformed boundary layer y momentum equation for 2D compressible flow is very simple. This we are familiar with, that it will be simple. Again, recalling that m infinity is not too high, only under such a condition this is valid. And note that how do you come to this del p del eta equal to 0 can be shown very easily, because in the physical plane the corresponding equation was del p del y equal to 0. So, if you apply this relation in order to transform it, then you have del p del eta into this quantity, which basically means that del p del eta is equal to 0. Therefore, the y momentum equation boils down to this. Coming to the concluding remarks, in this lecture we completed our discussion on 2D laminar compressible boundary layer equations. We discussed about the concept of self-similar and non-similar solutions of boundary layer equations. In the process, we also recapitulated the Blasius equation for incompressible laminar boundary layer over a flat plate, which we have learnt in our earlier courses on fluid dynamics. We discussed about transforming the compressible laminar boundary layer equations, and we looked at the x and y momentum equations through those transformations. Thank you.